First of all, it's a great pleasure to introduce this afternoon in the earlier slide session Professor Francisco CHINESTA, Paco CHINESTA, who is full professor at ENSAM Paris. He is also president of the French National Computational Mechanics Association, CNAM, and he is also a specialist of so many things. List all his area of interest. And also, I would like to say that Paco CHINESTA has an international recognition in many areas, and he has also received the silver medal of CNRS 2 years ago. And he is also honorary fellow of Institut Universitaire de France. And also, I would like to stop, please.
This is perfect.
Please.
This is perfect.
Paco.
Thank you very much. Thank you very much, Anthony. So good afternoon, everybody. So as Anthony mentioned, my name is Francisco CHINESTA, but I prefer that you call me Paco. And this afternoon we are speaking, I would like obviously to thank the organizers for inviting me, speaking about this topic that more than a research topic is my real passion in research that concerns a mix between the artificial intelligence and the physics-based models. And we call them hybrid twins. And this is a new alliance between physics and data manipulated by using mathematics or artificial intelligence. So obviously, this is a joint work with my colleague and friend, Elias Cueto from the University of Zaragoza. And even if I put only these two names, myself, Paco, and Elias Cueto, you can imagine that there are many collaborators, many young students and researchers that contribute in all the topics that we are discussing this afternoon. Obviously, if you have questions, please don't hesitate to send your questions, and we can try to adapt and to reply online if the questions cannot wait for the end of the session. My affiliation is Métiers, that is a high school of engineering in Paris, in a laboratory that is associated with the CNRS. And we are working in the context of an industrial chair that is the chair from ESI Group, that is a software vendor that is developing many activities in simulators, simulating physics, and also is introducing these new tendencies that we call digital twins, and in particular, in the context of ESI, they call them hybrid twins. And you are discovering during this afternoon all the things around these two keywords. The first keyword that concerns physics, manipulated by using model order reduction in order to obtain real-time feedbacks, but Anthony this morning speak a lot about that. And the other point that is quite present in my presentation today concerns the data manipulated by using the artificial intelligence. That is one of the topics that you are following in these journeys. So I will start with an introduction in order to present the engineering in the last century on the left, and the engineering in the new century, in this third millennium, on the right. I start with the image on the left, in which design in engineering obviously is to reach the performances, the prediction of the good performances. And obviously, as soon as these performances are ready, you can move to the industrialization. This means you can start to produce components, to produce parts, to produce objects, to produce systems. Obviously, in order to obtain all this, you need to consider four main protagonists. The first one on the left is the models. Why? because these objects are governed by the equations of physics. And for that, you need to take into account that the solution must fulfill these first principles and the equations of physics. I call them nominal. Why nominal? Because I expect that these models are describing the physics, the reality, but I'm never sure. The reality is the reality, our models are our models. And we are discussing today that sometimes models are good, sometimes are not good enough. And we are discussing on that. But obviously in the past, we assume a model. As soon as we assume a model representing the object, we need to introduce also the loadings in the more general sense, mechanical loadings, thermal loadings, etc., that we expect that this object will experience during its life. And this is again nominal, because I'm not sure about the reality of this object in the future in its life. So finally, loadings is the loadings that I expect this object will experience, but again, we are never sure. There are also data. Data is something very timely today, but in the past we use data, obviously, and experiments, obviously. Why? Because we need to calibrate the models. In the model, you know, there are parameters, and we need to determine these parameters before starting engineering. So we need experiments. We need to collect data in order to calibrate the models and to perform numerical simulation, that is the solution, the numerical solution with the help of computers, in order to obtain the final performances of your design. So this is all the ingredients: a model that we call nominal, a loading that we call nominal, data that serve to calibrate and also to validate the design, simulation in general performed by using powerful computers, and at the end of the day, we obtain the prediction of the performances. And if the performances are there, we can start producing the objects and we can continue with industrialization and with the use of these objects. So this was the past. Now we move to the right. You know, as is indicated in this slide, world is changing, is normal, is evident for all the presence this afternoon. Today, we don't sell aircraft engines. We are interested, instead of that, we are interested in selling hours of flight. We are not interested in something that we call electric drills. No, in fact, we are interested in good quality hulls. So we are more interested today in the performances than in the object itself. And this is very important because this is, for me, from my point of view, the main difference between the engineering in the last century and the engineering in the new century. In the last century, the object of the engineering was the product, the object, the design. In the new engineering, the object of the engineering is the performances, is the use during all the life of our design. So we are moving from something static offline to something dynamic online. And this is very important, and this implies radical changes. As we can illustrate in this image on the right, now we are not concerned by nominal models. No, we are concerned by the real system itself, the real system. And the real system at the present time, at time t. And we don't need to consider nominal loads. We know the real load that this object experienced, at least in the past, at times tau lower than t. And now, this is the job of the engineers. If I know the real system that is in front of me, and I know all the history of these systems, can we conclude on the state? This is called diagnosis. can we infer the future behavior? This is known prognosis. I would like to predict the behavior of my system at any time in the future, at any time tau greater than t. And this is the real object of the nowadays engineering. And as you can see, we are now concerned by the real system in the real life, and not only by designs that we produce offline, and as soon as they start to be produced, this was the end of the engineering. Now, no. The role of the engineer don't finish with the object. It continues during all the life of this object in operation, in service. So finally, we can describe in some keywords, and this is again my vision, the real domain of engineering, the real engineering in this century. First, we are treating the systems, as you can see in black on the left. We are treating systems that are the more and more complex. Oh, yes. We are speaking today not only about one component on one machine. We are speaking about Industry 4.0. We are speaking about a smart city. We are speaking about a smart nation. So finally, you agree with me, systems are becoming the more and more complex, the more and more large, not only in the time dimension, but also in the space dimension. And the reality is plenty of variability, plenty of uncertainty. And we need to treat the real systems complex, large, and many times uncertain. Okay, good. And what is expected on that? It is expected that we are not only interested in designing the system, we would like to learn from the system itself. During its life, the system produced data, and I would like from this data acquire a knowledge. I would like to learn from the system in operation. So this is new. In the past was only designing. Here we are trying also to learn. We are trying to monitor in order to anticipate. And this is more or less the word that I'm using in green. We are interested by the diagnosis, the state of my system now, by the prognosis, the state of my system a little bit later or simply later, in order to make decision making, the right decision at the right time. And this is finally the things that I would like to perform, these three words that are in green. And now the question is, and in order to reach this objective, what is needed? What is needed? Something very simple to write, relatively complex to ensure, is the three words that you can see in blue. You need to be accurate. Oh, yes, accurate. And you need to proceed fast. Oh, yes, because many systems today, you need to take a decision in the millisecond. In avionics, in the autonomous car, in nuclear plants, and in many other systems. So finally, accurate and fast. Oh, yes, this is normal. This is normal, but in the history, these two words, accurate and fast, have difficulties to move together. Why? Because when we are looking to be accurate, we take a lot of time in order to solve the model. This is the classical simulation based in finite elements. It's very nice. It's very accurate. But when you push the button in the computer, you need to wait hours, days, weeks. It depends on the application. But something is sure, in general, the response time don't allow to perform real-time control. So it's not enough, it's not fast enough. On the contrary, when we are looking to something that runs and works faster, in general, in the past, we degrade the model, we simplify the model, and now you can move very, very fast. But obviously, there is not miracle. If you are moving fast, this means that you are computing solutions that are not so accurate because you perform some simplifications in order to obtain the solutions fast. So finally, these two words are a little bit contradictory, and in the past we make a compromise between both accuracy and rapidity. My presentation today, and this is the main topic, is how to combine, how to create a new alliance between these two words that are needed in engineering. We need to proceed very, very fast, but we need to compute solutions very, very accurate. And all my discussion this afternoon concerns how to reconcile definitively these two words, accurate and fast. Okay, now that the main objective of my presentation is clear, I would like to come back to the two paradigms that exist. There is a paradigm, very, very popular in the last century, that we were the paradigm based, the models based on physics. There is another paradigm, a little bit more recent, that concerns the database paradigm. And I would like to analyze with you the strongest points of both and the difficulties of both, because obviously today there is not one that is perfect. If not, there is no discussion and we apply it. So obviously there is not optimal solution. And for this reason, a little bit later, I try to use both paradigms in order to solve, as I just mentioned, fast while ensuring the accuracy of the solution. So I will start with the physics-based models on the top. And I will refer to the image that appears on the right on the top. What is this? We have the behavior of a real system, a real one, that is the continuous red curve. And you have a model based on the science, based on the physics, based on centuries of works from our ancestors. And this model gives you the solution that appears in red, the discontinuous line. As you can see, the model is not perfect, no, but it's not stupid. It's close. The main tendencies are there. But we can see that there is a deviation, there is a bias, there is a gap that is increasing in time. And so this is dangerous, because this means that maybe now we are not so far, but maybe in 1 hour, our predictions are very, very far from the reality. So models are good, but there are some drawbacks, difficulties related to the use of them. The first one is the variability. In the real situations, there is an amount of variability that in general is not well taken into account in the models. The second one is the uncertainty. Oh yes, we know more or less the behavior of my system, but we don't know perfectly. Reality, and there are many things in the reality that we don't understand, that is not in our models, and we call all this uncertainty. And obviously, you know from the past, even if today, after the presentation of Anthony this morning, is not so critical, we know also that the solution of very high fidelity models take a lot of time, and one of the drawbacks is the computing time. When you push the button of the computer by using your favorite software, for solving a model in 3D transient, nonlinear, and coupled, you need to wait a lot of time. So the computational cost and the time that you need to wait to have a response are not so good in the case of physics-based models. And this means that it's very difficult using them in order to make real-time decision-making. So this is more or less the difficulty related to the classical paradigm, the paradigm that is related to most of science and engineering. Now there is another one that appears in this slide in the bottom. We have data, and we know that data can represent everything. Data is the reality itself. So if I can take an infinity of data, I will understand the reality. Oh yes, I have an image, a very precise image of the reality if I take as many data as needed. In the limit, an infinity of data. With an infinity of data, you can represent exactly the continuous red curve that appears on the right, in the top and in the bottom. Oh yes, we can. But infinity is reasonable. An infinity amount of data is reasonable. And the answer is not. This is not reasonable. Why? Because data is expensive. Oh yes, when you take the price, the cost of a sensor, sometimes it's very, very expensive. And obviously, putting sensors in your devices is not always simple. So this means that it's complex from a technological point of view, and the cost is important in the practical or from the practical point of view. So this is one problem, and for that, we reduce the amount of data. In this case, in the image on the right, on the bottom, we decide that more than infinite, we are taking only 6 data that are the small blue squares. And obviously, by assuming that there is not noise in the measurement, not noise, the measure is perfect, we can reproduce in these 6 points exactly the reality. The blue dot is on the red curve. And this means that we are taking a precise image of the reality in these points. But in between, as you have no data, the more reasonable thing is to make an interpolation. And the simplest interpolation is a linear regression that is moving from one data to the other. And when you take this representation of the reality that you obtain with 6 data in this case, obviously is the discontinuous blue curve. The solution, yes, it takes the tendency, but it remains very, very far from the reality. This means that in order to improve the representation of the reality, I need to consider much more sensors. And this is difficult because this is extremely expensive and in an industrial context, very difficult to organize and to implement. So obviously, we come from a mathematical point of view to explain with an infinity of data, I represent everything. Yes, I agree. But obviously, such a conclusion is mathematically correct, but from the point of view of the engineering is useless. So we can see that the main difficulties of the database approach is the amount of data that you need, in some cases, a lot of data when your solution is strongly nonlinear. The difficulty of explaining your solution, in the case of a model, we can explain why it runs, why it works. But when we obtain this discontinuous blue curve in the bottom on the right, my God, why is like this? So explainability is difficult. And you know very well that when something is difficult to explain, it's difficult to certify. And you know today that in many applications, in energy plants, in car industry, in the aircraft industry, if you cannot certify, you cannot make engineering. So this is also a difficulty related to the use of data. It's like a black box that is becoming the less and less black and the more and more gray, but obviously we cannot understand everything. We cannot certify everything. And the last difficulty of database approaches is the extrapolation. Why the extrapolation? Because when you have two data, interpolating between, this is a safe operation. You put even a straight line, and even if the solution is not a line, a straight line, you will be far, but not too far. On the contrary, if you have a parabolic profile and you move very, very far, obviously this solution is moving to the infinite. So extrapolation is very difficult. And in mathematics, in engineering, we don't like to extrapolate. We prefer interpolate, but not extrapolate. But as probably Antoni mentioned this morning, when you have a high dimensional parametric space and you take a sampling of the space, a design of experiments, you are taking few points in a very large space, highly multidimensional. And this means that you are almost never inside the convex envelope of this data. You are always outside. And when you are outside of the convex envelope of the data, you are in an extrapolation mode. And when you are in an extrapolation mode, this is very risky. So please, take this into account. Interpolating, why not? But extrapolating is really dangerous. And in database approaches, many times, in many circumstances, we are in an extrapolation mode. So simply, be careful. There is no problem. We can extrapolate in the life, we extrapolate every day. But when extrapolating, if you are moving or going too far, there are a lot of risk in the accuracy of your solution. So finally, I'm not happy with the first paradigm, the physics-based. I'm not satisfied with the database paradigm. So now the question is, there is something in between? And this is the hybrid engineering that I will treat with you during this afternoon. And I will start to introduce it before presenting the 3 or 4 main protagonists that will organize the talk today. For that, I will start with something that I call the fundamental equation. That is something absolutely great, absolutely evident, and as you are, or we are proving together, absolutely powerful. This fundamental equation reads like this. The reality, the real world, is equal to the things that you know, and this is the art of modeling. The art of modeling is all the things that the teachers use in the university in the different courses, plus the things that you ignore. Reality is the knowledge plus the ignorance. Why? Because the reality is much more than the things that you know, the models that we call the art of modeling that we developed in the last centuries, plus all the things that exist in the reality that you model ignore. So this part, we call them ignorance. Ignorance is all the richness that our model cannot capture, because even our or the most sophisticated models are based on some simplifying hypothesis. And this is the most important equation that I will develop during the talk today. But the important message, if there is one in my presentation today, is please remember in your life the fundamental equation of the human knowledge is based on this fact that the reality that exists around us is some part that we can explain from the knowledge that we have and something that escapes to this description and that we call ignorance, and we are trying to approach by using different methodologies, in particular, data and machine learning. This is coming, this is coming. And all this, we call them the hybrid paradigm. Why hybrid? Because like in the cars, there are two engines. Here is the same. We have two components. One component that I call analogic equations, the laws of physics, and a component that I call digital, that is the data manipulated by the machine learning, artificial intelligence. We are discussing on that. I summarize the hybrid paradigm in the figure that appears on the bottom on the right. You have your real system, the continuous red curve. You have your model, the discontinuous red curve. It's not perfect, but it's not stupid. There is a gap, but in any case, the solution is not bad. And as I just mentioned, when you subtract your predictions, your model, the discontinuous red curve, from the reality, this gap, this deviation between both curves, this is the gap, this is the deviation, this is the via, and I call it the ignorance. And in this case, the ignorance is something that is quite linear. Why quite linear? Because in general, the most important nonlinearity of the reality is captured by the model itself. And when the deviation is small, in mathematics, something that is small is linear or reasonably nonlinear. But obviously, the nonlinearity is much smaller than the linearity of the system itself. In this case, it's perfectly linear. It's never the case, but in any case, I would like to emphasize in this image that the ignorance, the deviation, is much less non-linear than the model and the reality themselves. And this is very important because, as in this case, if the deviation, if the ignorance is linear, this means that two data suffice to represent it. Is the first data and the last one in 0, in 1, the two small blue squares. And now I represent the interpolation, and the good news is, if you take your model that is not perfect, but not stupid, and you have two data to model the ignorance, that is the blue discontinuous line, and you put both together, you obtain the continuous red curve. This is the hybrid paradigm. You can make a better that in a physics-based model, you are making better that in a full data-based model. The first, because you improve and you fill the gap with respect to the data, because two data is enough to describe the ignorance, and then when putting with the physics-based model, you represent the reality. This is the advantage. The first one, you are making better that by using only physics. You are making better that by using only data. So this is very nice from this point of view. And there are other collateral benefits. The collateral benefits is you cannot explain the ignorance. Of course, by definition, the ignorance, you cannot explain it. Because if you explain it, it's because you know. And if you know, you model it. So I'm not trying to explain this ignorance, this means the gap, but I can explain the model. So at least the most important part in my modeling, I can explain it. And this is important because I can certify from the knowledge related with the model that we are using. And we can ensure that in any case, my predictions will be better. So this is also some collateral advantages of using this hybrid paradigm. Well, this is nice. And now I could summarize the three main protagonists of the twin family. The first one is virtual twin. This is only my point of view, but it's important that I mention that because it's coming in the later in my presentation. The first one, I call it physical twin, virtual twin, sorry, in which if P refers the physics and D refers the data, you can see a lot of physics, few data. This was the traditional simulation, but was also a twin, a representation of your system in your computer, but obviously with plenty of physics, very few data, only the one that serve to calibrate the models and to validate the predictions. On the other hand, you have the so-called digital twins, 100% data. Oh yes, but please consider a large amount of data because I just proved that in order to represent strongly nonlinear functions, the amount of data could be impressive. So a lot of data, a little bit of physics, obviously, there is always a little bit. And now this framework that I call hybrid, in which we have physics, we have data, and obviously, probably, this is the right alliance in order to obtain something that is in between the analogic world of the past and the digital world of the future. So this is one possibility to create this alliance between knowledge and data. Now it's time to introduce the main protagonists that I'm discussing during the presentation. There are 4 parts in my presentation. The first one is I would like to speak about data. Oh yes, data is important. Oh yes, data is important. And not any data. The data in which we are interested, the data for engineers, or from engineers to engineers. The second part is, in my fundamental equation, there is the knowledge and there is the ignorance. The second point concerns all the knowledge that I have. The model based on physics, the model based on the accumulated knowledge from centuries. This is the second part that I will treat, probably very fast, because this morning I realized that Anthony provided also a very nice introduction to model order reduction. So very probably the second point I will make some economies in the presentation. The third one is, okay, and now sometimes I will realize that there is a difference between the data that I collect and my prediction. The difference, we call it deviation, gap, ignorance. And in order to model the ignorance, I'm using machine learning. So the third point that I would like to treat with you is how to create low-cost machine learning. Why low cost? Because I have no data and I have no time. And if I have no data, because the data is extremely expensive, and I have no time because I need to create a model to take a decision in few milliseconds, obviously we need a sort of low cost machine learning. And for that, there is no miracle. There is no free lunch in the world. If I need to proceed fast from few data, I need to introduce knowledge inside. And this is the physics-informed machine learning. By introducing knowledge in the machine learning process, I can reduce a lot the need of data, and I can increase a lot the time for the response. So this is my sort of low-cost machine learning technologies. And after, in the last point, you can imagine we are creating this fundamental equation in which I'm putting together point 2 and point 3. The knowledge that is coming from physics, plus the data manipulated with the low-cost machine learning, is creating these twins that in particular I call them hybrid twins, because are something that is using both paradigms, the one of the physics, the one of the data. So I will start with the first point. We are speaking now for 20 minutes, maybe a little bit more, on data. What is a data? A data sometimes is something very easy, a temperature that you can measure with a thermocouple. Sometimes a data is a little bit more complex. For example, myself, the data of myself, the data is always related to a use. Obviously, for the police, the data of Paco is my identity card. I know that I have many reasons. I have a sensibility. I have plenty of things that are important, maybe important. But for the police, Paco is an identity card. This is one data, one man, one woman, one identity card. This is one data. And the data sometimes contains plenty of information, not always numeric. Sometimes the data is categorical, qualitative, subjective. In any case, multiple, this is the first word, heterogeneous, this is the second one, information. So this is a data, is my identity card, and it contains plenty of things that are there. So this is a data a little bit more complex than the data that is coming from a sensor when I'm measuring the temperature. When we are measuring the temperature, the data is very easy. I measure a temperature, 100 degrees. I measure another one, 200. I can make subtractions. 200 minus 100 equal to 100. I can make additions. 100 plus 200 equal to 300. By my God, I take an identity card. I take another one. How to compare? So this is difficult. How to compare data? Comparing data when these data are real numbers, this is okay. But comparing data when it contains plenty of heterogeneous information, my God, comparing implies a metric. The metric is very easy to understand in a Euclidean space, but I don't know what is the space in which I can introduce a metric to compare identity cards. So this is the difficulty that we are addressing in the next minutes. Finally, a data sometimes is very clear. Sometimes a data is quite rich. Okay. So we continue discussing a little bit of data when data is easy to understand, easy. Forget for one moment the identity card, and you focus in data that we can measure because it's a real number. And now imagine that this data is bidimensional. You can represent this data in a two-dimensional space with an horizontal and vertical axis as it appears on the left. In data science, we like a lot to put the data in clusters, in groups. Why? Because like in society, when someone is in a group, has similarities with respect to the members of the group. So this is natural, and at the same time is a little bit risky, because from a social point of view, this has important consequences. But in fact, from a quantitative point of view, we would like to take all this data, all these points that appears in the image on the left, and I would like to decompose or to put this data, I decide, in 3 clusters, in 3 groups. This is called clustering, putting the data in groups. And for that, imagine that there are no colors. I put the color after dividing in groups. You can imagine that at this moment, there is not red color, blue color, and green color. All the dots are black. Imagine for a while that. If someone asks to divide all this data in 3 groups, I can use an Euclidean distance as I sketch in this image. And now I try to divide the data in 3 groups in order to ensure that all the data that is in this family that appears in red, any data is closer to the center of gravity of the red family than to the center of gravity to the other families, the blue and the green. And this technique is called K-means. K-means is dividing, organizing groups of the data with this criteria that is based in an Euclidean distance in general, in which we try to organize different groups such that all the data in one group is closer to the center of gravity of the group than to the center of gravity of all the other groups. And as soon as I divide the space, in this case, in 3 groups, I put the red, the blue, and the green color. But the color arrives after creating the groups, not at the beginning. And for this reason, we create groups without supervision. It's based only in a metric that is a distance, that in this case is the simplest one. And we call unsupervised clustering. Other times, the clustering is supervised. For example, in the case on the right, we are classifying the data that we have, and in that case, the color is known from the beginning. We have a family of blue and a family of green, and we are looking for the best frontier, the best interface that will separate the 2 groups. We are trying to put all the blue from one side, all the green for the other, and we are looking for the red line in this case that is the best to separate the 2 families. And again, in order to separate, we need a concept, we need a metric, we need a distance. And in many cases, we are using an Euclidean distance, or maybe we are using nonlinear kernels in order to perform nonlinear classification. But in any case, the important thing is we are manipulating data that is easy to compare in a linear or nonlinear case, but easy to manipulate. So in the equations on the bottom, you have for K families this concept of trying to decompose the data in the K sets, SI, such that we are minimizing this cost function that is the distance, and we need to define the norm and the distance between one data and the mean, the center of gravity of the family. And on the right, you can see we are trying to minimize W, that are the coefficients, in this case, of the linear the linear function w times x minus b equal to 0, that is in this case the equation of a straight line. And why minimizing w? Because in that case we are looking for the line that maximizes the distance with respect to it of the blue and green points. And like this, you are quite insensible to the noise, because when maximizing the distance with respect to the border, you are sure that it's easy to produce a classification in a very safe manner. So finally, we are minimizing W with one condition, that is that the product of the quantity of interest, that is the color 1 and minus 1, 1 for the blue, minus 1 for the green, multiplied by the equation must be greater than 1 in order to be sure that you have this separation. And after, as soon as you separate, the classifier is directly the sign of the equation of the straight line. So this is something that is very usual. You can find this in Wikipedia, in any book of data science. This is not the main message in my work. My main message is, okay, why not? I understand that. But I would like to compare data when the data is a little bit more complex. I have two identity cards, and I would like to measure the distance between the identity card. And this, you agree with me, this is not easy. This is not easy because I'm not in a vector space. And obviously, it's difficult to measure what is the distance between Martin and Chevalier. I don't know if even this question has sense. But obviously, in general, when manipulating data that is coming from industry, it's difficult to measure distances in many cases. And if I cannot measure distances, it's very difficult to clusterize, to classify, to use regressions, to use plenty of things. So this is important. And for this reason, we are speaking not about identity card, but we are speaking about problems in which we need to manipulate data that is a little bit strange. And for that, I will introduce in a few minutes something that we proposed in the past that we call to vet. What means this? This is an application in which, as I cannot take distances in one space that is a space of representation, I will create a map in order to move all the data to a vector space. And in the vector space, I can compute distances, and now I can apply any technology. So the important thing is, when I'm not in a vector space, the first step is moving to a vector space, and then we can use most of the existing technologies. How to proceed? Imagine the representation on the left. These characterize forming processes in the composite industry, and you have one product, one piece that you are creating is related to a kind of material. Oh yes, but the material, what is the name of the material? I don't know. Epoxy, polyester, thermoplastic, polycarbonate. There are commercial names that is difficult to put in an axis. So we decide to put polyester, epoxy, polypropylene, etc., etc. But I define an order in order to put all these names in an axis. After there is the employee name. Oh yes, there is Anthony, there is Paco. I will put Anthony, Paco, Cecile. I will put all the people in this axis. But it's difficult to put this in an axis because finally there is Anthony and Paco that are very close because I decide to start with Anthony and after with Paco. So this is a problem because finally the distance, that is an hypothetical distance, is not a physical distance in this system, depends on how I distribute the values in the corresponding axis. And after there is another one, that is the time in which I put my part in an oven at a certain temperature. So finally, what is a part? A part is something that is produced with a material, with an employee, during a certain time at a certain temperature. This is like cooking. You are using ingredients. You are the name of the person that is producing the receipt. You have the time in the oven, and you have the temperature of the oven, and you are creating cakes. And after, you can taste the cakes. When it's good, you put green. When it is medium, you put blue. And when it is horrible, you put in red. Obviously, for the cookies, but also for the part that you are producing, at the end, there are some parts that has a very good performances, others medium, other very bad performances. So we need obviously to take this into account. The question of the industry is, Paco, I don't understand. Because finally, there are 2 points here, the blue and the red, that are very close. Oh yes, they are very close. And finally, one is good and not the other. What is the problem? Because in data science, when data is close, they share the same behavior. The response is very easy. Yes, but how you distribute the name of the employees in this axis? How you introduce the name of the material in the other? Is you, when you are distributing the names, that you are creating a distance that is absolutely artificial. So this and this are not close, are not far. I don't know, because I don't know which is the distance that I introduce in my axis. So in order to solve this problem, we decide to take each one of these data. One data is one part, and one data is constituted by 4 informations. Type of material, name of the employee, time, and temperature. This is the 4 information that constitute each one of the data that is related to an elaborated part. And obviously, I have also a label. Label is the quantity of interest, OI. That finally is the color, green, very good, red, very bad, blue, medium. And the idea is, okay, I will take all the points yi, and I will move to another space that is a vector space in which the coordinate axes are xi. And each one of these points is mapped in one point on the right side. The question is, okay, Paco, but there is a problem. You don't know the point on the vector space, x is unknown, and the mapping, that obviously in general is nonlinear, is also unknown. The only thing that you know is y, that are the data in the representation space on the left. So the question is, we cannot create this mapping in order to push all this data on the other side. Yes and not. Maybe we can. How? Because, sorry, I upset. I can make something very easy, is to ask, I would like to push all the data on the right diagram with one condition. If they are very close, they have the same performances. Medium, good, and bad. Here we have a distance. If something is close, we have the same performances. If something has different performances, we are putting far one from the other. For example, the green from the blue and the green from the red. We need to push apart. We need to push apart data that corresponds with very different performances, trying to group the data that are related to the same quantity of interest, to the same performances. We would like to put together the blue, the green, and the red. And how to write this is the question that appears in the bottom. I would like that when I send yi to obtain xi and yg to obtain xg, the mapping is wi minus wyg, the norm of that, because in this space, we are in a vector space and I can compute a norm. This is the distance between xi and xg, the norm, but we have a norm. And we would like that this distance between the points on the right is proportional to the difference of the quantities of interest, the color in this case. If the color is the same, this is almost zero, and we need to push the points very close. If the colors are very different, xi and xg must push apart, and this means that we are creating groups that obviously differentiate depending on the quantity of interest. And for that reason, we call it code-to-vect, because we are moving from a codified space to something that is a vector space in which, as I just mentioned, we have all the properties that allows to use standard machine learning technologies. Well, do you have enough data? Oh, yes, because this equation that appears on the bottom applies to any pair IG. When you have many data, all the possible combination of one data and all the others produce plenty of equations, and plenty of equations is enough to create or to learn to extract the matrix that define the mapping W. And as soon as from this equation in the bottom and all the equations, because there is one equation for each pair, I and G. As soon as I have all the equations, and there are many, as much as combinations of the data, we can obtain W. And now as soon as W is known, I apply W in each original data to produce the data in the vector space. So this is one technology that allows to manipulate data that is very heterogeneous in order to move to the right space in order to make safe operations. As soon as W is known, we can use now for in real time taking decisions. Oh, imagine that one day the guy in the industry asked me, Paco, do you think that Peter, by using an epoxy, by putting it 10 minutes at 200 degrees, will obtain a good part or not? I represent the data. As you can see, is Peter, is epoxy, is 10 minutes at 20 degrees, and this is the black dot. I apply to this black dot the W that I learned before. If I arrive very close to the green, go. If I arrive very close to the red, no. Don't stop. There is something that is clear. Maybe is Peter not the best choice? Maybe it's not the epoxy, or maybe there is another choice of the temperature and time in order to make things different. So this is the idea, and we are trying to summarize or to make an example, a real example of the use of this theory. For that, I'm considering an industrial case. This is Gestamp. This is the B pillar in the car. And this B pillar, in order to protect you when you have a crash, an accident, they evaluate the intrusion. The intrusion is the displacement of the structure inside the cabin at 4 different points, as you can see in the image on the bottom, at the level of the head, at the level of the thorax, at the level of the abdomen, at the level of the pelvis. And this is something that is important in order to be sure that the driver or the occupant is protected. And so in the choice of this part, there are many parameters. There are 2 parts or 3 parts that are encapsulated. We have the thickness of the inner part that is in green. We have the thickness of the patch that is in the middle. And you have the thickness, the ductile zone material grade, and the ductile zone size that are the 3 parameters related to the outer part. And so finally, you have 5 parameters, and depending on the choice of these 5 parameters, you will obtain different intrusions at these 4 levels: head, thorax, abdomen, and pelvis. And finally, the idea is to take the best choice in order to reduce the weight of the car. This is very important, but obviously in order to protect the driver or the occupant. And for that, I need to choose the best choice of parameters. But like in the previous case, don't forget, there is something that is a thickness. Oh, this is nice, a thickness. This is also a thickness, good. There are 3 thicknesses that are numbers that I can manipulate. But now it's more complex. There is the ultimate tensile stress. This is an stress. This is not a thickness. This is not geometrical value. This is an stress. And you have also the size of this ductile zone, that is the green part in the red component, that determines the quality of this part to dissipate energy. And so finally, this is another thing that is a distance, but is different to the thicknesses that we compared before. So we have a problem of a certain richness to manipulate that. So people perform a design of experiments. Anthony introduced this morning the design of experiments, and in particular, they simulate 22 cases by using a high-fidelity solver for the crash simulation with different values. This is the design of experiments, this table, related to different choices of these 3 thicknesses, the size and the grade of the material. And for all of them, they has a curve that appears in the representation on the right on the top, in which we have the intrusion in time. The intrusion in time, you can see that at the beginning there is nothing. After the deformation start, we reach the maximum, and after there is the elastic spring back and the intrusion reduce a little bit. And finally, we have these curves. There are 22 curves, each one related to the choice of these 5 parameters. And the maximum intrusion is the time at which you have the maximum of these 22 curves. And obviously, this maximum intrusion, in this case, I consider only the head. I would like to create a model that describes the maximum intrusion, the maximum of these 22 curves with respect to the 5 parameters related to the B pillar, the 3 thicknesses, the grade, and the ductile zone size. And for that, as we are manipulating these 5 quantities, we are creating something like a percentage representation. We are putting thickness 1, thickness 2, thickness 3, the grade, and the size of the ductile zone. And after we have many data, 22, and the colors in this case are representing the maximum intrusion at the level of the head. Obviously, in this representation, the distance is not well defined because we are mixing different things: geometrical thickness, positions, stresses, and finally, even by normalizing, you are losing a lot of physical information. And the idea is to move to other space in which similar things similar intrusions are close and very different intrusions are far. This is the idea when using the equation in the bottom in this slide. And when we are applying this, finally we obtain, please refer only from the six small images, please refer only to the one that is on the right on the bottom, in which the label of this figure is upper intrusion value. As you can see, good news, independently of starting from this very heterogeneous data, when I move to this space that is a vector space, you can see that the yellow are together and the blue are together, and in between there is a certain degradation with this light blue, green, black, yellow, and light yellow. So this is good news because, as just mentioned, the code2vect is trying to organize the data in the vector space such that similar things are close, different things are far. And this, in this case, the quantity that controls the distance is the difference in the intrusion at the level of the head. So this is good, and I can represent this in a two-dimensional space, and this is nice because this data that now is in a vector space can be used in order to make plenty of things. I don't treat now this case. I will stop in this slide, but obviously all this data is the same that the one that you have at the beginning, but in the right space in order to take distances that we cannot take by using the original representation. And now, before moving to the next step, we are also discussing a little bit the other 5 sub-images when it represented parameter 1, number 2, number 3, number 4, and number 5. What is this? This is exactly the same representation that the last one, that the one that I just discussed, the one referring to the upper intrusion value, but instead of using a color that indicates the extrusion, we are using exactly the same representation, but now I change the color and I put the color related to parameter number 1 in the first image, parameter number 2 in the second one, number 3, number 4, number 5. And I will prove that this representation have a lot of information, a lot of knowledge. Why? Because check please with me, parameter 1. Color yellow and blue are mixed. This means that there are points in which the upper intrusion is yellow and the parameter 1 is yellow or blue. Conclusion, parameter 1 is not correlated with the upper intrusion. Number 2, oh yes, in the regions in which the upper intrusion is yellow, here we have yellow or we have blue. Conclusion, the second parameter is not correlated directly with the upper intrusion. And the same applies for parameter 4 and parameter 5. Parameter 3 is a very nice surprise. Parameter 3 is when parameter 3 is very small, blue, the intrusion is very high, yellow. When the parameter 3 is very high, yellow, the intrusion is very small, blue. So finally, parameter 3 is correlated with the upper intrusion in an inverse manner. So finally, this representation is nice because it's equivalent to find a non-Euclidean distance, but we proceed by mapping the data in a right space in which things that are close have the same properties, and when the property is very, very far, the points are quite far. So this is the first interest. The second one is, as you can see, you can analyze the correlation and the fact of one parameter is or not useless So for that, this is a very valuable representation. Next step, we are moving to other kind of data. This is one kind of data very important in industry. Now we are moving to another kind of data, also very important in engineering. Two in particular, time series, left top, microstructures, left bottom. And now the question is, if I have a time series and I have another one, is it possible to compute the distance? Oh my God. I think in the universe, there are not two exactly identical time series. Even if you take your heart and you record all the functioning today, tomorrow at the same time, you will have something similar, but not identical. So the question is how to compare things that are similar in a certain way, but are not exactly identical. The same for a microstructure. Take one image from one foam, take another one. They will be similar, but pixel to pixel, are radically different. So if we need to compare time series, or we need to compare microstructures, we need to discover the right metric in order to address that. And this is extremely important. Like in the room in which I'm speaking you, outside there are trees. There are many trees. All these trees are very different because they have different sizes, different branches, different leaves. And obviously, they are similar in a metric because I recognize that all these guys are trees. So this is more or less the idea. There are something that is invariant, and the thing that is invariant is the topology and not the data itself. So for that reason, in our research, we decide, instead of using a Euclidean matrix that has no sense, we decide to use something that inherits the invariance properties of topology. And we try finally to resume a time series in one image in a vector space that we call persistent image. And this is something important because all the time series that are radically different but has the same topology exhibit the same image. The same for the images. All the images of a foam will be radically different pixel to pixel, but the persistent image will be more or less the same. So finally, we are attributing to the time series and the images a short, mathematically we call it the persistent image, persistence in the topological sense, from a more friendly sense. For me, this is a sort of QR code or passport that characterizes the data that you have. So I'm trying to extract from images, from time series that has a very rich content of topology. We are trying to condensate all this topology in these images that finally describe in a very concise and a very complete way all the topology of the data. And obviously this is goal-oriented. I call it QR code or passport. And the good news is this image is in a vector space, and I could apply any kind of regression, any kind of technology in data science. I could even apply on it a convolutional neural network in order to learn, but not directly from the data, but from the persistent image associated to the data. I would like to show you how to extract a persistent image from a time series. And for that, I consider this very simplified case that is on the left, that is a time series that is evolving in time in the sense that is represented by the blue line. And now in order to extract the topology, I'm trying to identify, to collect, to extract local mean and local max that are neighbors. Local mean and local max that are neighbors. We have one, 11, 14. 11 is a local minimum, 14 is a local maximum, and they are neighbors. So I select them, and this is the two red squares. After there is the 7, 9. Oh yes, the 7, the 7 is a local minimum, the 9 is a local maximum, and both are neighbors. And we have the 9, 10. 9 is a local minimum, 10 is a local maximum, and they are neighbors. And this is the two blue squares. And now we represent this topology in another diagram that we call the persistence diagram, in which in the horizontal axis I put the minimum that we call birth, and in the vertical axis I put the maximum that we call death. Why? Because the maximum is always greater than the minimum, like the death is always greater than the birth. And like this, you can see that I represent the points, the three topologies, the 7, 9, the 9, 10, and the 11, 14, that are the three blue dots that appears in the figure on the right. And we call it persistence diagram. Obviously, you have only the upper bisector. The diagonal is things that appears and disappears immediately. So is the topology that does not persist. And as you can see, this is a representation of the topology. And finally, you lost one information is when this mix max, min max appears. We have one, the other, and the other, but we don't know which is the order. The topology is there, the order in time is not there. And this is very important because we are interested only in invariant properties, and invariant properties depends, obviously, something that is independent of the time translations or rotations. As soon as you have this, we can move further and we can define another diagram that we call a lifetime diagram, in which we take the 3 points. We have the same representation. In the horizontal axis, we have the birth. In the vertical axis, we have the lifetime. This means death minus birth. This means the distance of the point to the diagonal. And when you represent this, again, you have these 3 points that represent the content of topology of the data series. This is not comfortable because finally you have some kind of Dirac delta masses that are very localized, but we like to have something more regular, like in SPH, in smooth particle hydrodynamics, in which each one of the particles are regularized, smoothed by using Gaussian kernels or other kind of functions. And here is similar. We use a kind of convolution. We associate to each one of these points a kind of Gaussian kernel. And now you take this space, you can create something like a QR code. In this case, we take a box that is composed by 20 per 20 pixels. And now the idea is to take each one of the pixels and to evaluate the accumulated functions that are coming from the regularized kernels related to each one of the particles. And at the end, you have this kind of images in which you have the blue, the pink, the yellow, that in a certain way, like in this QR code that we call the persistent image, translate the content of topology of the time series that we are considering. Obviously, the same apply in 2 dimensions when we are considering images and not time series. And in that case, you can consider 4 points. There is no topology because you have 4 points. But now if you consider that you have a vision that is controlled by this radius R that appears on the top on the left, and you are increasing R, at a certain moment, A and B are mutually visible. B and C are mutually visible. C and D are mutually visible. A and D are mutually visible. And we just create a whole. There is the topology that appears at this moment because we create this whole. And this whole persists until the radius continue to increase, and at a certain moment, A and C are mutually visible, and the whole disappears because now is fully occupied by 2 triangles that just appear. And this means that we can assume that there is a topology that appears at a certain moment and disappears at a certain moment. We have the birth and the death. And we can again associate to different microstructures the persistence diagram at the end of the day, the persistent images. And you can see that if you take many snapshots of the microstructure that appears on the top on the left, they have all them independently, that the cells are never exactly at the same position. The persistent image is almost the same. And obviously, when you are changing the topology, the persistent image is changing. And this allows to have a kind of QR code that characterizes the microstructure that you are considering. So this is quite important because you can perform this, you can make diagnosis, and I try to explain in this slide, in which I'm focusing in some applications. In the first one, we have different families of rough surfaces. And obviously, you have many families. The surfaces are radically different. And obviously, even when you are in the same family, the rough surface is different from one point to the other, but from the topological point of view, they remain very close. This is the important news. So this means that if we have 16 suppliers from suppliers of a composite surface, the rugosity is very different, even for each supplier, depending on the region in which we are measuring. But the good news, from the topological point of view, even if the surface, the rugosity, is changing from one point to the other, in one part that is coming from even the same supplier, all the persistent images are almost the same. But the persistent images are changing from one supplier to other. And this means that if we have 2,000 surfaces, by using the persistent image, I can apply a classification or a K-means in order to distribute all the surfaces, 2,000, in 16 families. As you can see, this is the confusion matrix. I put all the surfaces in the right family with respect to the supplier, and I commit only 1, 2 from 2,000, I don't know, 700. I make only 2 mistakes in which I assume that one surface was from supplier 0 and was supplier 14, and in the other case, I assume that was the supplier 4, and finally this was the 7. But except 2 cases, this means that even if it's very difficult to compare time series, it's very easy to compare the topology of this time series. And the topology of the time series is something that accounts for the intrinsic nature of the data. On the right, you have another application, industrial application, in which we have drivers. these drivers are, you can control the displacement of the head of the driver or the occupant. And if you are applying a vibration in the basis of the seat, you can see that depending on the state of the driver, is tense, is relaxed, is tired, the displacement of the head is different. And so we obtain time series very complex. And in the past, we tried for many years to compare this time series. It was absolutely impossible. And one day, and we have not too much data, and one day we decide to take this time series to obtain the persistence diagram. Now you understand everything. We obtain the persistent image. We obtain all this. And now we can characterize, for example, that this kind of image that appears in the slide is related to one driver that is tense. And like this, from the movement of the head, I can conclude with a very good accuracy, as appears in the slide, what is the state of the driver, and only by analyzing the topology of the time series related to the vibration of the head. There are no models, there are no physics, there is nothing. We apply the same, in this case, in the left, to the faults of a system. And you can see there are different time series in the top. There are two behaviors that are nominal. Nominal means there is no defect. And you can see there is no defect. My God, these two images are radically different. The images, sorry, the time series are radically different. So the idea is I cannot compare time series at this level because all the time series are different. So the idea was, okay, we are moving to something that is more invariant, more intrinsic. For example, we are computing the persistence diagram and the persistent images. And good news, see please on the bottom, when it's nominal, the signature is almost the same. And when there is a fault type A, B, C, D, E, there is a particular pattern that expresses the appearance of this kind of fault. So this means that if we identify a pattern with a behavior, and obviously this is almost the same for all the behavior that has the same kind of topology in the corresponding time series, this means that I can make pattern recognition in order to provide a real-time diagnosis. So the idea is to summarize the different behaviors in a persistent image, defining a sort of catalog, fault catalog or dictionary. And as soon as I have a time series that is coming, I compute the topological content. And depending on the topological content, I move to my catalog, to my dictionary, in order to identify the persistent image that is closer to the one that I just obtained. I'm in a vector space. I can compute distance in an Eulerian or Lagrangian way, in the sense of the optimal transport, or in the sense of the classical distances, but obviously using distributions and optimal transport is better in order to identify which is the closest image to the one that I just received, and depending on the answer, I can make a diagnosis in real time. And the same, as just mentioned, applies for complex images. And this is very useful in order to make online control in processes, to make pattern recognition. And a little bit later, we are using it also in order to introduce these persistent images in order to create models. I will stop here. I propose that we take a little bit of time for a break. And in the next part, I will move to manifold learning before starting the two parts that are more easy to introduce, that are the ones related to modeling based on physics, modeling based on data. I will take more or less a half hour on each one of these topics. So I propose we stop for the break. We meet again at 4 o'clock. And at 4 o'clock, we move to the next 1 hour and a half in order to cover the end of manifold learning and moving to database and model-based learning. Thank you, and see you in 20 minutes.
Thank you very much, Paco. So 50 minutes for a break.
50 minutes.
Okay.
Perfect.
Super.
Thank you.
Okay.
Okay. Perfect. So we try to continue. So we start by discussing a little bit more about the manifold learning concerning the intrinsic dimensionality of the data for almost 20 minutes. And after we are moving to the machine learning and the model order reduction, even if this morning with Anthony, you analyze and you treat the question of constructing reduced models. So we start with this slide that you can see, in which you have data that I represent in the image in the top with two components, coordinate or the output 1 and the output 2. They represent some outputs that are coming from sensors or that are coming from a model. You can see you have all these points and you think that you are in a 2D space and that the number of coordinates that you need to represent these points are 2. But as you can see, all these points are in a one-dimensional manifold that is the line that passes through all the points. And if we can express that all these points, as you can see in the top on the right, depends on only one parameter that we call C, that I'm not sure is something that combines certainly O1 and O2, but we can conclude that my data contains only one parameter and can be parameterized with only one parameter. If you give me the value of C, I can obtain the value of O1 and O2. So this means that many times you have rich data, in this case not so rich, you are in dimension 2, and you can see that you can reduce the data, and this is, we call it data reduction, in the sense, if data is correlated, please remove the correlations. And we can see here that we can reduce from a dimensionality 2 into a dimensionality 1. Obviously, this is an operation that is very well known, and the name of this is the principal component analysis, PCA, that consists in order to find this coordinate, the only thing that you need is to rotate, to change the frame, in order to move to the blue one to the red one that appears on the bottom on the right. And you can see that after a kind of rotation, all the data is aligned in only one axis, and the other one, the projection of the data in the other is absolutely 0. And this proves again that even if at the beginning you put all your data in a two-dimensional space, finally you are in a one-dimensional manifold. And the operation in order to construct that, we call it the PCA, and it consists in a linear transformation in order to align the data in one of the coordinate axes and remove the other. And this is important. The only drawback is when you are in the top, O1 and O2 has a physical sense. For example, temperatures and pressure. On the contrary, when you are moving the axis, you are rotating the axis, you agree with me that the red ones is a combination of the blue ones. You are projecting the blue into the red. And so this means that this red axis mix the blue ones. So you have an axis, in this case, that could be a linear combination of temperature and pressure. So you have only one parameter, but you cannot measure it. There is not a device in order to measure the temperature pressure. You have devices to measure the temperature, to measure the pressure, and this is the representation in the top on the left, but you have nothing in order to measure something that has only dimensionality 1, but is not physical in the sense you cannot measure it directly. Like in fluid mechanics, when we are speaking about the solution of a flow depends on parameters like the density, the viscosity, the velocity. Okay, in principle, you think that you have 3, but in fact, you have only 1 that we call the Reynolds number. The Reynolds number is the only one parameter that affects the kinematics of a flow. The problem is you can measure the viscosity, you can measure the velocity, you can measure the density, but you cannot measure with a device the Reynolds number. It's only one parameter that is a combination of parameters that you can observe, that you can measure. And this is important because sometimes you reduce, you are very happy, but finally by reducing, even when you are happy, you are arriving to something that is mathematical, but is not physical in the sense, is something that you cannot have access with a direct measurement. We move to the next step. And in this slide, you can see the definition of something that has different names: proper orthogonal decomposition, principal component analysis, Carnot and Love decomposition, or singular value decomposition. All this is very, very close. And in order to express that in a more general way, you take the second line. We assume that the data xi is composed by capital N informations, the components of the data. You can put for the different data 1, 2 until capital M. This data, this arise in the columns of a matrix, the matrix Q, and you can compute the eigenvectors at the eigenvalues of Q transpose, that is the covariance matrix, and you will obtain capital N couple eigenvalue eigenvector, lambda 1 V1 until lambda n Vn. And in general, if you are in a manifold that you can obtain by linear transformation, and this is very important, this means that finally there are a small r eigenvalues different to 0, and the remaining one from lambda r plus 1 to lambda capital N are equal to 0. And this means that finally your complexity, your data, is in a manifold of dimension r that is much smaller than capital N. And this means this is data reduction by removing all the correlation that is present in your data. That means that even when the data contain many, many components, are apparently in a high dimensional space, sometimes by using a linear dimensionality reduction, you can embed in a linear manifold that the dimension is much smaller. So sometimes, apparently, like in this case, I could ask you, what is the dimensionality of this data? And now your answer is, oh my God, if I take all this data that apparently is two-dimensional, because I am trying to rotate the axis, like in the PCA, and by rotating, I never align all the data in the same axis. So your conclusion is, apparently now, you have data in a 2D space, and apparently the complexity of the data is 2D because there is no correlation. And, oh yes, it's still one-dimensional, but the manifold is non-linear, and PCA don't work in that case. We need to speak about non-linear manifold learning, in which we need to learn that this data is one-dimensional, is in a manifold of dimension 1, but is non-linear. But if you consider this a spiral and you consider the curvilinear coordinate C, you can express all the data by using one coordinate, and this coordinate is this curvilinear coordinate C in this case. But obviously, you need to use adequate techniques and not the ones that only works in the linear case like PCA. And there are many of them. You can find all these in the web. You have the LLE, locally linear embedding. You have the kernel-based PCA. You have the local PCA. You have the TSNA. You have plenty of the technology able to extract the intrinsic dimensionality of the data, even when this data is in a manifold, but is non-linear. And in this case, please don't apply PCA, apply other technologies that are more robust in that case. One example, in order to make this in engineering, I would like to share with you one analysis that was performed with my colleague Elias Cueto, in which we consider different cars. This is the cars that we are trying to make an aerodynamic analysis, and we put all these cars because the shape of a car, how many parameters you need to define the shape of a car. You can imagine that if they are the geometrical parameters, the CAD parameters, there are hundreds. But the question is, yes, but maybe these hundreds are extremely correlated from the point of view of the shape. And to make this, we decide to put all the vehicles, all the cars, inside this box that is in green, that represents a mesh. And after we decide that the shape of a car is taking each node in the mesh and computing the distance with respect to the surface of the car. This is very easy if you are using level sets, because the level set related to the surface of the car, the value of the level set that take a zero value on the surface of the car represent the distance of each point in the domain to the surface of the car. So by solving this equation, we can compute the distance of each node of the mesh to the surface of the car. And now you agree with me that the car number 1 is given by a shape that can be parameterized by the distance of the capital N nodes of the mesh, the distance to the surface of the car. And now if you have different cars, you have different points, because when you are changing the shape, the distance of the nodes of the mesh to the surface of the different cars are changing. And for this reason, you can represent the shape of a car as a point in a space of dimension capital N that represent the number of nodes of a mesh in the outside the car in this box that I represent. And now the question is, are all these points in a curve? Wow, this is excellent. If it's the case, finally you think that you have capital N, but you have only one. Or maybe with all these points is in a surface. In this case, you have 2. Or maybe it's inside a volume. In this case, the dimensionality is 3. And we need to find what is the dimensionality of the space. For that, the idea is how to discover that, as you have in this slide, you have points that are in a 3D space, but you can see that they are in a 2D manifold, and you need to discover it even when you are working in very high dimensions. And in that case, you cannot perform this with your eyes. Like in this case, everything is easy because I can represent, but when you are in a space with hundreds of dimensions, you cannot perform this at the eyes. And for that, I would like to comment 2 technologies, the LLE, and after we are moving to the kernel PCA. The LLE is summarized in this slide, in which you have many dimensions, as before, capital N, and you have data that are the black and violet points. And now the idea is you take one of these points, for example, the red one, you agree with me that even if the manifold is nonlinear, it's locally linear. Something that is nonlinear is you take a point and the points that are very close, you are in the tangent space, and the tangent space is linear. So the idea is to express that the red point could be expressed as a linear combination of its closest neighbors, that are the violet ones. And this is the first equation on the right. Each point, even in a nonlinear manifold, can be expressed as a linear combination of the closest points, because you are more or less in the tangent space that is linear. And now if you write this for any point, you have that you would like to find these weights Wij that relates the influence of data G on point I. You put all this to a square and you make the sum for all the points, for all the data in your system. And you try to minimize this. If you are in a linear manifold, the minimization gives you a 0. You can minimize and obtain a residual that is 0, because each point can be expressed in a linear way from the neighbors. If it's in the nonlinear manifold, obviously you can minimize, but you don't obtain a 0, and you will obtain a compromise, the different Wij that allows to express each point from the closest neighbors. And as soon as this is ready, now you know which is the relation from each point to the closest neighbors. In this case, the red with respect to the violet, but after you need to repeat it for all the points in the set. And now as soon as you have something that has a dimensionality that is the tangent space that is not so big, we can embed this in a low dimensional manifold that is the Yi, and here I represent the Y by a small n coordinates that is represented on the bottom on the right. And now, as in order to take one point and the vicinity and move into the radius space is a linear transformation. In a linear transformation, the W, the weights are constant. And so this means that in the reduced manifold, in the slow manifold, the relation between Yi and the closest neighbors use exactly the same W that we obtained in the first equations. And now we are looking for the coordinate, the reduced coordinates in the manifold Yi, such that the sum of the expression of each Yi with respect to the closest neighbors Yg by using the same weights Wij is minimum, and with this you obtain the coordinates in the slow manifold in the radius space. So this is the way that LLE perform in order to reduce the data and to move from a high dimensional space to a slow manifold in which the data can be reduced. And one application that Elias Cueto performed was the one that I comment by using the cars. He analyzed all the cars that was available. We discovered by using the LLE that all these cars, the shapes, are living in a space of dimension almost 2. We create the manifold, and if I stop my presentation here, the good news is if one day you discover a new car that you never analyzed before, the idea is to determine the shape, to move this shape in the manifold, to locate in the manifold the points that are close to it, because if you are very close, you are in the tangent space, and you can perform a linear interpolation, and by performing a linear interpolation, you can obtain the streamlines that I represent in the car, in the red car in the bottom, and I superpose these streamlines without any calculation, by simply determining the shape, putting the car in the manifold, and interpolating the aerodynamic solutions from the closest neighbors. This was the use in order to perform real-time computations and in order to obtain in real time the drift and the lift and the drag that finally it was in real time by this technique of manifold learning. This was real time, and the error that we committed in the calculation of the drag and the lift was lower than 3%. The same applies for the levers. You have many levers, real ones, and in order to determine what is the shape of the lever, now you know everything, we put each lever in a box, we compute the level set with respect to the surface, and we compute the distance of each voxel in this box to the surface of the lever. And when you compute this for many levers, you obtain the representation that appears on the right on the top. And now the question again is, what is the dimensionality of that? And by applying again the LLE, we arrive to the result that the shape of a lever can be represented by 4 parameters. And now the good news in the video, the third one seems more or less the volume. The second one is a particular distortion. The third parameter induces this distortion in the lever. And the fourth one induces another deformation. And the good news is each one of you, your lever is a combination of a particular position of these 4 sliders in the video. So finally, even if the geometry of the lever is very complex, it's absolutely incredible, but 4 parameters are enough in order to represent the geometry. Like in the car seems very complex, but finally more or less 2 parameters are enough in order to describe the shape with respect to the lift and drag calculation. So this is very important in the sense something could seem extremely complex to describe, and finally is not so complex, and the operation that we need to employ in order to extract this intrinsic dimensionality are the technologies based on the manifold learning. Well, this is for the LLE. I would like to introduce the KPCA, the kernel-based principal component analysis, in order to explain how to proceed with this new technology. As you remember, I introduced the image on the left. If you have many points in a space, in a high dimensional space, R, capital D, obviously you cannot represent it by using the dimensionality is 2, but you cannot apply the PCA because PCA is linear manifold learning, and obviously with a plane you cannot describe all the data. In non-linear manifold learning, yes, but PCA, this is the issue, because as just mentioned before, it's a technique that only works in the case of linear manifolds. So this is more or less my vision of the kernel-based PCA. And I take these photos in the Musée d'Orsay in Paris, in which you can see the image on the surface of the water. The image is extremely nonlinear. It's nonlinear in 2D, but things are extremely linear in 3D. And this is the physical sense of kernel PCA that establish that many things that seems nonlinear in a dimension, in a space, if you project in another space much more rich, things become linear. And as soon as things become linear, you can apply the PCA. So this is only something that we are using in order to apply the PCA when you are in a non-linear setting, And the idea is move first to a space of higher dimension and after reduce the system. So from a mathematical point of view, you are in a space of dimension capital D, the image on the left. You move to a new space in dimension capital Q, and Q in general is much higher than D. And after, as now your data is in a linear manifold, you can apply the PCA in order to reduce to a small d. And in general, this small d is lower than the initial capital D. And in this case, we are reducing data. We are making manifold learning-based data reduction. But, and I will explain this in a few minutes, sometimes we could take D higher than D. We are not reducing. We are not reducing. And this is very important, and I will come back to this, because it's one of the most original things that I would like to share with you today. So in general, this is used in order to reach a small d that is lower than capital D. But sometimes the dimensions in the target space could be even higher than the dimension in the original one. And I will discuss this with you in the next slides. So example, imagine a problem that is the problem of a backlink of a beam. The beam has a length of L, the width is B, and the height is H. We are applying a load P, and we know this is coming from the Euler theory, that when P reaches a value that is proportional to BH cubed divided by L squared, there is the backlink of the system. So now the question is, imagine that this is the physics. The physics depends on three parameters, L, B, and H. But the circumstances is you have only two devices to measure. And you decide to measure L and to measure H, but you never measure B. And what is the consequences of this? If you represent the critical load, that is the color in the representation, for each value of H and for each value of L, that are the values that you measure, sometimes there are many colors that are mixed. Sometimes you obtain a P that is important, and sometimes the P is very small. So finally, as the colors are mixed, we can conclude that our problem is statistic, and sometimes I obtain a value, and sometimes another value. But I'm not happy with this. We like in engineering deterministic systems, and in deterministic systems, fluctuations are coming from other the physics, but in general, we don't like that models today give this result and tomorrow another one, because if not, it's very complicated to make prognostics. So the question is, this is, and we understand, these colors are mixed, because finally, the color takes also into account that there is one dimension that is changing, that is B, that I never measure. And as I never measure B, these points that seem that for the same H and the same L, they have different P, we understand because these points have different B. But the problem is we never measure B. Why? Because we take the data, we take too few data, only two, when our problem depends on three. So this means that in some cases, there are internal variables, there are hidden variables. If I don't consider this variable, like in plasticity, if you never consider the plastic deformation, it's difficult that if you measure the total deformation and the stress, you cannot understand plasticity. Here is the same. You cannot understand backlink if you take only the length and the height, because it depends also on B. But you never measure B, because for you this data was irrelevant, And finally, you have a problem, a serious problem, when looking at this slide. So in that case, we are using the KPCA. As you remember, the figure on the left, first, we take the data, we push to a space of dimension capital Q, and after we apply the linear PCA because we are in a linear manifold. And in general, I use this technique to reduce. But sometimes, as it appears in this discontinuous circle, we can stop at D higher than capital D. And in this case, there is a good news. When instead of 2 dimensions, as I considered before, the length of the height, we consider 3, and this is coming from the kernel PCA. The kernel PCA, when we consider 3, there is a very good news. That is, there is not mixing the colors. There is not mixing the colors of the critical load. And when we use a color that scales with B, the colors are degraded. And this means that KPCA first inform us that we need another dimension that I never introduced in the model. There is a hidden variable that I need to model or to measure. This is the first. And the second, a criteria that is when stopping in the right dimension, I start with 2 dimensions, L and H. And finally, kernel-based PCA inform me it's better to stop in dimension 3. So this means there is another variable that we should measure or that we should model. In our case, we know is B. In our case, in general, we don't know. But in our case, we know. If I take the data in this 3-dimensional space and I use in order to represent the color related to the B, we can see that the 3rd dimension is related to B. But in our case, it was easy because I know that this variable is important. In general, this is the most important difficulty in the choice of the variables. Now we are moving in the opposite sense. We consider that we are in an hypothetical universe different of this one, our world, and we assume that we have a physics that depends only on 2 variables, H and L, but as I have 3 devices to measure, I measure also B. Why not? Why not? Now, the opposite case, the previous one was, we consider 2 data, and the physics depends on 3. Now, I take 3 data, and the physics depends on 2. What is the consequences of this? We start with 3 data. You can see I'm introducing B's and B's and B's and B's, and in the equation of the backlink, in this hypothetical universe, the backlink does not depend on B. And when you perform this, you are looking for a function, the backlink load, that depends on B, H, and L, because you are providing 3 data. And the question is, in this physical situation, it only depends on 2. And now we apply again KPCA. We project, we reduce, and now good news. The final dimension is smaller than the original one. I start with 3, length, H, and B, and KPCA inform me, my friend, your physics is 2-dimensional. You need only 2. You need only 2. For me, it's clear because it's in the equation that I'm using in order to generate the data. But the kernel-based PCA informed me about the necessity of considering only 2 and not 3. And now, how to discover the data that is useless? This is very easy. As soon as you recover the 2-dimensional manifold that is nonlinear, that PCA provide, you can use the colors with respect to B, and you can see that the colors are totally mixed. This means that B could be high or low for loads that are high or small. And obviously, if you are using the colors related in this manifold with respect to the height and with respect to the length, you can appreciate the color degradation. That this means that there is a correlation between the height and the length with respect to the backing load. On the contrary, the width, in this case the B, is absolutely decorrelated from the loading, the critical loading. So this is all for the first part that concerns the data. Very rich, but this is the most exciting part. The part that follows is interesting, of course, but is more easy to discuss, because the point number 2, Anthony this morning introduced many concepts, and the 2 last points are very easy and will be covered very fast. So after this bigger part that concerns the data, we are moving to the first term in the fundamental equation, that is the part that concerns model based on physics. This is the first part. Data now is more or less understood. Data is complex. Data is heterogeneous. We need to express the data in the right system. We need to discover and to learn the right metrics. And very important, we need also tools in order to see if, with respect to the physics that I'm trying to model, the mechanisms that I'm trying to model, I introduce too many data or not enough. And this is the last part that I just treated. Now, as soon as data is more or less clear, I'm moving to the second part, that is the first term in this equation, that is the physics-based model. That we call the art of modeling. And finally, we can imagine, and this is the PGD that Anthony introduced this morning, we assume that we have a parameterized problem in which you have a partial differential equation, a linear or non-linear differential operator that is the calligraphic L, that acts on the field U, that depends on space X, on time T, and the problem is parameterized by a set of parameters mu1 to mu_m. And all this equal to a term that is the loading of the system, the calligraphic F. And the PGD, we are trying to create these virtual charts, this vademecum, this abacus, that is the solution of your problem at each point, at each time, for any choice of the parameters. And in order to circumvent the curse of dimensionality, as the dimension of the problem is increasing, because it was 3D transient, and now there are many other dimensions that are the capital M parameters that we are introducing in order to circumvent this curse of dimensionality or the combinatorial explosion. We are using the separation of variables that express that something that depends on X, time, and a series of parameters can be written as a sum of functions that depends only on X, xi, x, function that depends only on time, capital TIT, and a series of functions that depends each one in only one parameter, the functions capital P, IG, that depends on the parameter mu G. And obviously I changed the representation. You can introduce this separator representation in the weak form of the partial differential equation. There is a little bit of acrobacy from a mathematical point of view, and after some gymnastic, you are right to compute this multidimensional solution that constitute the virtual chart or the vademecum that is no more than the parametric solution for any choice of the parameters. So there are many technologies, and this we published plenty of papers with these techniques, but we never apply them because finally introducing this in a commercial software, this is crazy. And for this reason, we prefer to use alternative solutions. In the alternative solutions and in the chair that we have with ESI group as Métiers, we decide to create surrogate models, meta models of the system. And for that, it's very easy. We are using an sparse design of experiments that are trying to cover in an sparse way the parametric space. For each one of these points, as Anthony mentioned this morning, we create a high fidelity solution that we can compress from one high fidelity solution. We can extract the modes that depends on space, that are the modes in blue in this image, the vertical ones, and the modes that depends on space, on time, sorry, that are the horizontal ones, and the tensor product of all them represent the space-time solution of the problem. In order to make this decomposition, you can apply any of the technologies that exist, the POD, the PGD, the CURE, the AIM, or the cross approximation. And as soon as you have a reduced expression of each high fidelity solution, we can add the parametric dimension by using an adequate parametric modes. And finally, the tensor product of modes in space, modes in time, and modes in the parameter allows to obtain this parametric solution that describe the solution at each point, at each time, and for any choice of the parameters. Technologies, there are many technologies. We are using the technologies that we propose. Obviously, there is the classical polynomial regression. That is good, everybody knows. The problem is when the data points, the sampling is sparse, using sparse data with a little bit of noise and increasing the degree of the polynomial to represent nonlinear functions, you obtain something that I represent on the left, on the bottom, something that is the blue curve, that obviously represent all the data that you have, but present high oscillations. And in the world of manifold learning, this is called overfitting. So polynomial regressions has the tendency to overfit, and this is very difficult to control. And the other inconvenient, the other drawback of these technologies is by using global polynomials, it's very difficult to represent problems that contains many, many dimensions, tens of dimensions, or hundreds of dimensions. For that reason, when we are treating high dimensional spaces, we make always the separation of variables. And for this reason, in all the columns that you have on the right, you have the PGD. PGD means separation of variables. So the metamodeling is not something that we propose. Metamodeling is something that is very, very classical. The only thing that is original from our point of view, and this is our job, is to combine technologies for creating surrogates with the separation of variables that is at the heart of the PGD. So we are using the PGD, separation of variables, combined with orthogonal basis, in the case of the SSL, hierarchical basis. The problem is the basis is hierarchical. When we are increasing the number of dimensions, the quantity of data that is needed increase too much. For this reason, the SSL sparse subspace learning-based PGD only works well when the degree of the polynomial is quite reasonable and when the number of dimensions remains quite low. When you are increasing the number of dimensions or you are increasing the complexity of the function, we need to move to regularize sparse representations in which the sampling is sparse because we are working in a space with tens or hundreds of dimensions. And obviously, in order to obtain richness, treat many dimensions and avoid overfitting and take very few data, all these ingredients are crazy. Few data, richness in the solution, avoiding overfitting and having plenty of dimensions, the only possibility for us of address all this is by combining the separation of variables with sparse regularizations, that is the S that appears many, many times. And in general, we are using a regularization that is called elastic net, in which there is a part of rich that is based on a regularization in an L2 norm, and a part that is based in the L1 norm that we call lasso. Rich is avoiding overfitting, lasso is looking for sparsity in order to obtain rich solutions at very low cost with very few data. And for that reason, there are many members of the family. If some of you are interested on that, I could send a paper that we just published in which there are all the details on all these technologies. And the last one that we are implementing today is the so-called ANOVA PGD, in which the advantage is we are looking for the separation of variables, we are looking for something sparse, and we are looking for using a base that is orthogonal. And this is the case that is employed in the ANOVA analysis, in which, at the same time, by using the Sobol coefficients, we can extract what are the dimensions that are important with respect to the solution. So this is a summary of all the technologies that we are using in order to collect solution in some points of the parametric space, combine all them to create the surrogate, more or less like Anthony. Probably the technology is a little bit different, but the objective is exactly the same. Create a chart, a parametric model, in order to change the parameters and in real time obtain or particularize the solution. The technology probably is different, but we have the same objective that Anthony discussed this morning. Obviously, I have no time to speak about interpolation, but if you are interested in the slides, I discuss a lot about the use uniform meshes, random meshes, noisy random, etc. in the determine, overdetermine, and undetermined case. Also the use of orthogonal bases like a Legendre in all the cases that I discussed in order to appreciate the robustness and in order to appreciate the risk in using standard representations or approximations when you are creating your regressions. So I don't consider this, I have no time, but obviously you are interested, I can share with you the presentation is some experiments that we perform in MATLAB in order to understand all these points that are important. That is, are we using regular meshes in the parametric space or sparse? Are we using orthogonal polynomials or standard ones? What happens if the data is fluctuating because there is a noise? What happens if we have more data than the degree of the solution, or we have less data than the degree of the solution, or we have the same quantity of data than the degree of the solution? So we analyze in the previous slide all these combinations in order to take effectively some receipts that we are using in the next. Well, I will spend only 2 slides, and after we are moving to the applications, in order to imagine that you have this problem that appears in the screen. It's a problem that depends on 2 parameters, mu and eta, and you have a field that is U that depends on mu and in eta. Imagine that you know the solution of U when mu eta, take the first value, mu1, eta1. You have also the value of U when you consider mu2, eta2, and you have also the value of U when you know mu3, eta3, that is U3. And now the question is, okay, this is very good, but I would like to know what happens when we have another value of mu eta that are different to the first, second, and third choice. In that case, as you have 3 data, the most reasonable approximation is consider a linear regression. You can write that U that depends on mu and eta is a coefficient A that express the constant part or contribution to the solution, something that is linear in mu and the coefficient is B, and something that is linear in eta and the coefficient is C. And now you have obviously three unknowns, A, B, C, and you have three data because you know that for mu1 eta 1 you have u1, for mu2 eta 2 you have u2, and for mu3 and eta 3 you have u3. So three equations for three unknowns, you can compute A, B, C, and like this you have your linear regression. The problem is, but the linear regression is very poor. We cannot make better. And one possibility to make better is, okay, I'm using a very rich approximation basis in which we consider up to the second degree. My basis now consider 1 mu eta mu squared mu eta eta squared etc. until the end. Now we have nine terms, 9 monomials, and this means we need 9 coefficients to be calculated. But you have only 3 data, because we are in this case. So the problem is, in 3 data, we have 3 data, and we have 9 unknown coefficients, each one affecting to one of these terms. You have an infinity of solutions. Oh yeah, you have an infinity. And the computer takes one in this infinity, and it depends if you are using the backslash, if you are making an optimization problem, if you are using a pseudo-inverse. Depending on the technology that you are using to solve this underdetermined problem, you will obtain one solution or another one. And the main risk, and this is the main risk that appears in my previous slides, that I don't discuss with you today, is sometimes we can obtain this kind of overfitting, that is the discontinuous red line, that proves that you represent the data. But in between the data, you have a very strange behavior because you prefer to have something that is smooth than something that is highly oscillating. And this is called overfitting in the community of machine learning. My idea is, can we use rich approximations without having this effect of overfitting? And the answer is yes. We are using a very rich approximation in which we consider all these terms. We have only 3 data. This means there is an infinity of solutions. And this means that now in this very rich basis, my solution can be written as a sum from 1 to capital N. In our case, capital N is 9 because I introduce only 9 terms, or some coefficient that I need to compute, and different functions of mu, jet, eta, that are the different monomials that appears in my approximation basis. And now, as you know, the solution of this is not very well defined. There is an infinity. Your program, your MATLAB, your backslash, your pseudo-inverse is choosing one, and the risk is the overfitting. How to limit the overfitting? By regularizing. The regularizing means I would like that in the points that I know I'm looking for the last equation in the bottom, I would like that when we are in one of these 3, or when we are in the 3 data that I know, I would like that my approximation, that is very rich in 9 terms, approach the data that I have. And this is the sum from G equal to 1 to 3 of the particularization of my approximation in the 3 data points with respect to the 3 data that is known. And in order to avoid that there are plenty of coefficients C that try to include a little bit of contribution of each term in the approximation basis, and as the degree is increasing and increasing, the solution will be very highly oscillating and obtaining the overfitting, I introduce a regularization that is the term on the right in the bottom, that is that lambda, the sum of the absolute value of all the coefficients, is a penalty in the regularized formulation of the approximation. This is the L1 norm. And in order to introduce this in an easy way, we can use the lasso. And this means that this penalty tries to limit the number of non-zero coefficients Ci. And this means that like this, we can obtain rich solutions. We can limit overfitting. We are looking for sparsity. We have few data. And finally, we have all the conditions that are needed. And obviously, this is the main slide in my discussion, but this is not my proposal. There are many people that propose this kind of approaches. This is the sparse regularization. And our only contribution to all this business is when, other than this expression, we are using a separated representation of the solution at the heart of the PGD, because in our case, we have not only mu and eta, we have hundreds of parameters. Sometimes, in one of the cases that we are working now, we have 800 parameters, and we have only 10 calculations. 10 data for 800 parameters. For this reason, we need to regularize, okay, but we need to use the separation of variables that is the main contribution of the PGD. And we are not discussing all this, where you have all the details related to this slide, and we are moving directly. I don't consider this, or yes, I'm considering a little bit. Okay, so this is the way that we are using in order to compute parametric solutions. And now there is something that is new. Sometimes the parameters are not so deterministic. And the parameter, we must consider that a parameter is much more described by a statistical distribution that is characterized, if we assume normality, but we can change the description, by an average, a mean value, and a standard deviation. This means, for example, in this case, you have the Kropotki's law, in which you have a relation between the plastic deformation and the stress. And this depends on three parameters that are K, epsilon 0, and N. And obviously, depending on the choice that you are making, you have in the bottom on the left the different traction curves that you obtain from the beginning until the fracture. Obviously, in the reality, when you are using a material, the material is not always the same K, the same epsilon 0, and the same N. Sometimes, when you are making a robustness analysis, you need to consider that when you are using or you are constructing your part, you are never sure what is the real K, the real epsilon 0, and the real N. You know that the average is 1, but you have probably also something that is the standard deviation that the supplier characterized many times. And now we need to construct a parametric model that takes into account not only the value of the parameter, the mean value, but also the standard deviation. And when we are applying this to the traction test of this kind of coupons, specimens, we are obtaining something like this. I check if it runs. When you change the mean value, the plateau is increasing. Changing the other, the fracture is increasing. And now when you are increasing in this parametric model, the standard deviation, you are creating a corridor in which, if the statistic of the parameters are these ones, you are sure that at 95% of probability, your curve is inside this corridor, and the point at which the specimen breaks is in between these two values, that is the corridor for the breaking process. So we can move from a parametric solution to something that is more statistical, in which you can propagate uncertainty, and in particular, you can provide a robustness analysis. And now you can even put all these solutions inside the sensor, and this is very important in smart sensing, in the digital twins of the sensor, in which at the level of a sensor, in which we are measuring in the RTM, for example, the pressure, you can know that the pressure in this point depends on many parameters. the permeability of the preform, the thickness of the mold, and it depends also in a parameter RT that depends on the kinetics of polymerization in this case. And now in this sensor, if everything is going well, and the parameters are the one that I consider, and the standard deviation is 0, we should obtain this curve in the sensor. But we know there is a variability in the permeability, there is a variability in B, and there is a variability in RT. And this means that depending on the variability that you will analyze in your process, in your material, finally you know that by changing the value you obtain this, and when you are changing also the standard deviation related to each one of the parameters, you are computing parametric corridors. You are computing a parametric statistical solution that can be used in order to know that if something is inside this corridor, everything could be on control, but obviously you are very far from this corridor. This means that something in the system is not going well. So this is something that is very easy to introduce in the system. Sometimes the variability is not coming related to the model itself. Sometimes the variability, like in this slide that I'm showing here, is coming because data has a noise. Now we are speaking about variability, not in the parameters of the model. We are speaking about variability in the data itself, because you are using real sensors, and in real sensors there is a fluctuation, a variability that could be important. So the idea, in order to create again a parametric solution that takes into account the noise in the data, is imagine that you would like to construct a linear regression, and you have only one parameter, and you are looking for a model that is y function of x. This means y is ax plus b, a linear regression. The parameter is x, and the output, the one that you are measuring, is y. And you know some data, you know for different values of x, xi, the value that you measure that is yi. But I assume that obviously in the next slide, not in this one, the noise will appear. So if there is no noise, in this slide there is no noise, in order to compute the parameters, if you have more data than the degree of your regression that is linear, you know that we are trying to define a cost function that is the difference between yi and the linear regression applied on xi, and you are trying to minimize it, and this is no more than the least square. So finally, you have much more data than the richness in your solution, and for that, the linear regression or the regression that you are computing is related in this case to the standard least square. Now we assume that this is not the case. Now we have noisy data. And as you remember, this was in the top, the cost function that I consider in the case non-noise and a linear regression. Imagine that you are, again, looking for a linear regression, but now the data is noisy. We define the same function, but now we are trying to express that the difference between the data that you collect with respect to the linear regression should be in agreement with a normal distribution of the standard deviation that is related to the data. So finally, it's very easy to express that you are looking for a regression such that all the data that you have distribute with respect to the regression in order to be in agreement with respect to the statistical distribution of the data. And like this, instead of computing a meta model, again, in another way, this is a nonlinear regression computed by using the support vector regression, like the PGD could be. Now we are representing the model, the regression in blue, and we are representing the interval in which you have 95% of the probability to have all the data, and this is given by the pink surfaces. Well, when we finish with all this today, and I don't spend a lot of time because this was explained also by Anthony, using probably a little bit different technologies, but not too different. We can apply this in very crazy cases, like in crash with these customers, Volkswagen, Renault, Stamp, Mitsubishi, Hyundai, etc., in which we have modeled with 5 million elements, 20 parameters. We have only 20 runs. And as Anthony presented this morning, by changing the different sliders, you can particularize in the points that you want. In the right, you have a welding, and this was also a problem that treated by Anthony. We learned by using sysweld, and now we have this meta model, and we are changing the different coefficients in order to appreciate the impact of the parameter, obviously, in the different thermomechanical fields. So this is something that today is quite mature. In the figure, in the next one, sorry, I try to move to the next one. Is in the top on the right, you have an airbag. I cannot represent it, but it's a movie, that's not in importance. This is thermal comfort, and you can, in a cabin, in a car, change the different parameters that are related to the temperature outside and the flow rate, and in real time, obviously, particularize the temperature inside. We have the other video that is coming on the top on the right. This is for forming or thermoforming, and in this case, there are also some parameters that appears. You can see this is completely agnostic, and we are using this technology that today exists in a cloud application of ESI group. Everybody can use, and finally, depending on your parameters, depending on your physics, at the end of the day, you arrive to a kind of parametric solution like this. In the bottom on the left, you have a crash test. This is public because this is the structure of the Yaris, and this is public. And there are different parameters that are related to the thickness of the different parts. And now in real time, you can change the parameters that you want. And obviously you have dynamics, you have elasticity, plasticity, damage, and fracture mechanics. You have everything. And on the bottom on the right, you have a problem in turbulence. And we can change the angle in the real part, or we can change the geometry. And in real time, we can evaluate the lift, the drag, and obviously we are interpolating solutions that are related to the turbulent flow. New things in which we are working in parametrical optimal transport. Why? Because there are many solutions in physics that localize. Imagine in the figure on the left, on the top, you have a solution for a parameter that is the blue one. You have another for another parameter that is the orange one. And what happens if you take the parameter in the middle? If you take a standard interpolation, you have the green one. That is the half of the blue plus the half of the orange. And I don't like this. I prefer something that is more or less the half, but located in the middle. And this is a problem for interpolation because this is not an Eulerian interpolation. And now the idea is, can we introduce optimal transport, that is the Kanterovich and the Monch problem? Can we introduce this in a parametric setting? And the answer is yes, we combine everything. And now we have transport combined with parametric solutions. And in that case, in a very proper way, by using parametrical optimal transport, we can move solutions that localize. In this case is flows. In other cases is fracture mechanics, when you have cracks for one parameter in one position, for another parameter in another one, and we would like to have a crack in the middle when you take the average of the parameters and not two cracks if you are interpolating in a standard way. So we need to interpolate correctly, and today optimal transport or our works that create this kind of parametric optimal transport is a very valuable solution. Finally, when we are treating systems quite complex. In this case, it's a landing device, and we can create a parametric model depending on the landing conditions, and you can see all the stresses that you introduce in the landing device because the landing conditions. Now you can create these three parametric models that you can couple by using Simulink, Simulation X, or Modelica to a system engineering model. And the good news is you can obtain 3D resolution at the rate typically of system engineering. And this is important because we are making better than system engineering, and we are making very, very fast with respect to standard simulations. And when treating system of systems, our proposal is create a kind of parametric transfer functions, not parametric solutions. Parametric transfer functions means that the input are also parameters. And like this, you can create this kind of assemblies in order to configure systems. And we call this technology the Lego PGD, in which you have 200 pieces of the Lego, and each one has 4 parameters. You can solve your problem with 800 parameters as a problem of assembling of 200 transfer functions, each one involving 4 parameters. So you are creating this. The parameters are the parameters involving the component and also the inputs. And as soon as you arrive to the assembling of these parts, you are enforcing the equilibrium, if it's usual in mechanics, and for that you obtain the displacement at the interfaces that are compatible to the force equilibrium. And like this, you can treat very complex problems, even in the nonlinear regime, in order to consider the crash of a car, but the car is represented by 200 Lego pieces that corresponds to the 200 components in the structure. Well, now we prove that solving physical models in real time is not a challenge, and this was clear even this morning in the presentation of Anthony. My second point is the same that the one that presented, or a part of the one that presented Anthony. And solving physics in real time, today, everything is not ready, but finally we are quite mature. We know we have an expertise, and we can solve very, very fast physics. The problem is, sometimes the physics that we are solving is not accurate enough, because, as you remember, the fundamental equation, now this, the first term in the equation, the art of modeling, the physics-based models, this run in real time. Oh, yes. But if the model is not good, finally we are computing very fast something that is not very good. So now the question is, can we work a little bit on the deviation that I call ignorance in order to model it? And in order to model it, I need to proceed with techniques a little bit low cost, because we have not a lot of data, and we need to be able to produce data-driven models very, very fast and from few data. If it's not the case, if you have a lot of data and you don't need to proceed very, very fast, there are plenty of solutions from the neural network that runs perfectly, but in general needs a little bit of data. And in my case, in the case that we are discussing, this data does not exist. So we are trying to introduce the physics-aware or the physics-informed neural networks, the physics-informed artificial intelligence. We are trying to learn the ignorance, that is, the gap between the reality and the model-based predictions in real time, very, very fast, and from very few smart data. What means smart data? The right data at the right scale, where and when, in the best places at the right time. So this is the difference between big data and smart data. Smart data is informed by the physics. If you are asking me what is the temperature today in Saint-Étienne, if you give me 2 thermometers, I will put one inside the room and one outside. like this is better if I put both outside or both inside. And this is due, I know a little bit, I have experience, I have knowledge, and I know that in general, temperature is not the same inside and outside. And we are using this knowledge in order to place the thermometers, the thermocouples in the right place. So finally, when you are informing the data by using physics, in general, you place the data, the sensors in the right place. You know, in Saint-Étienne today, the temperature is not the same in the morning, at noon, and this night, but if you know a little bit physics, if you have some knowledge, if you know a little bit about the physics in the weather, you know that the temperature in Saint-Étienne is not changing every millisecond. So it's not necessary that I record the temperature every millisecond. I can take 3 in the day, in the morning, at noon, in the afternoon, and maybe in midnight. So far, for data with 2 thermocouples, one inside and one outside, it's not necessary that I put 1 million thermocouples and I record the temperature every millisecond. This is stupid. This is big data. This is big or very big stupid. So the idea is to use the knowledge in order to conduct the data collection. Take the right data at the right place at the right moment. Unlike this, data is not so abundant. This is better for the collection. You make gains in the cost because you don't need to take 1 million, and you are treating the data that is not so abundant. So this is more or less something. It's clear that the models can be enriched by using data, but it's also important to note that data become smarter if we are using the knowledge that we have. So we need to alleviate, we need to create something in which finally data and physics are not in opposition. They could help mutually in order to have a very nice framework. So what about trying to model things in an intelligent way? There are many possibilities. There is a lot of work at this moment by introducing knowledge or physics inside the neural network, the deep learning or the machine learning. For example, the PINN, P-I-N-N, physics-informed neural network from Kardekakis in Brown University, for example, among many others, that are trying to drive the learning by using the physics. Here we are, in collaboration with Elias Cueto, we are more focusing in introducing thermodynamics in the learning. Why? Because when we are working in Hamiltonian mechanics, we have a very nice framework, and this was extended in irreversible thermodynamics in the case of dissipative processes, in which you have a state is in the right part of the slide. The state is Z. Z dot is the evolution of the state in the time. And you know, from Hamiltonian mechanics, or for the generic in particular, because there is the Hamiltonian and there is the dissipation, we know that the evolution of the state is given by one matrix that is coming from the Hamiltonian, and this is symmetric, and that concerns the gradient in the state, phase state of the Hamiltonian, the energy of the system, plus a matrix that is called the dissipation, that is symmetric and positive semi-definite, that concerns the gradient of the entropy. And now the only thing that we need is from data, we need to learn L, we need to learn H, we need to learn M, and we need to learn S, knowing that there are many consistency conditions. The Hamiltonian don't produce dissipation, and the dissipation, obviously the gradient of the entropy acts in a very particular way on the energy. So by using these consistency conditions, finally you can, from the data, you can start to extract L, H, M, S. And finally, when you finish the learning, you don't need many data. You need data, of course, but there are many things that are in this equation you enforce that the energy is conserved. You are enforcing that the dissipation is produced, and obviously independently of the noise in the system. And like this, you are computing or you are calculating integrators that are stable. And obviously, this is in order to enforce the thermodynamical consistency. We can use, for example, when using neural networks, we can also enforce by using the data, by using the architecture of the neural network, or in the loss function, you can enforce symmetries, framing difference, the convexity of some functions like the yield and plasticity when needed, and the Noether theorem in which symmetries finally and conservation are related. You can introduce plenty of knowledge, and when you are introducing this knowledge, finally you learn very, very fast, and you obtain integrators that are very robust. And this is the main aim of all this. You are creating a framework in which you learn faster, and the things that you learn, you conserve the energy, you produce the entropy, and producing entropy when needed is very important, because from the noise in the data, you learn something that don't produce entropy, you have an integrator that is unstable. So finally, this is very important in order to introduce first principles in the learning process. And obviously, when you have a system that is very large, like in the mechanics of continuous medium, the state is very rich, you need to reduce. This is like model order reduction, like in the PCA, in which you need to discover the slow manifold, the intrinsic dimension that is much smaller than all the degrees of freedom that you introduce in the description of the state. You can perform manifold learning, as I introduced in the first part of my talk, or you can use an autoencoder. Why an autoencoder? Because the autoencoder uses the encoder and the decoder, and the internal layer has a reduced dimension, a reduced size, that more or less represent the dimension of the state, the dimension of the intrinsic dimension of your system. And finally, as soon as you arrive at this level, you introduce the structure preserving neural network that tries to enforce, as you can see on the right on the top, all the thermodynamical consistency. And now you are reducing, you are fulfilling physics, and after you come back, obviously, to the physical state. By reducing like this is less physical than by making other technologies, but this is very powerful. And obviously, in order to introduce most of these constraints in the learning process, we are working by modifying the loss function in the neural network in order to learn fast and to obtain integrators that are stable. So Beatriz Moya, the colleagues of Elias Cueto of the University of Zaragoza, we try to learn from not too much data the movement of a fluid into a container, different fluids, non-linear, water, glycerin, blood, these are non-Newtonian fluids. We learn from the data some experiments that we perform by using SPA, for example, but at this moment we are learning this by using experiments. We learn the model, and as soon as the model is learned and is stable, obviously, now there is something that is nice. The container is real, the hand is real, the fluid is virtual. And we are introducing a virtual fluid in a real container, and you can see the fluid is making the things that are expected depending on the movement that we enforce to it. And here there are not equations. There is not Navier-Stokes equations. There is nothing. There is only learning, the learning process, but in a thermodynamical setting. Obviously, the more knowledge you have, the more robust models you can create. Last point, and we have 10 minutes to finish. We are speaking a little bit now that the data is rich. that we understand a little bit the richness. Physics-based models, we can solve very, very fast. This is the surrogate, the meta model, the virtual chart that Anthony introduced this morning and I introduced also this afternoon. The data-driven models, yes, but in order to process fast and from few data, we are using technologies a little bit low cost and very informed as much as possible by the physics. And finally, we are trying to put all together to create these virtual, digital, and hybrid twins. So this is the last part. When we add this to this, it results the so-called hybrid twin. So hybrid twin is something that is a fusion of the last century that I call the analogic knowledge, analogic because it's based on the equations of physics that constitute the virtual prototype, that we can solve very, very fast with the technologies of Anthony or the technologies that we introduce, that we can introduce in very complex systems and that we can manipulate in real time. And all this is the so-called virtual twin that I introduced at the beginning. And this is all the last century knowledge. This is the physics-based model. On the right, you have the data. What data? Not the data to construct the model. Only to model the ignorance, only to model the deviation. As soon as this deviation is ready, we have the data, we apply physics-informed machine learning in order to obtain the model, we introduce in the system model, and we obtain the digital twin, but only for the deviation. And now there is a dialogue, there is the sum of both, that proceed in real time, and the result of this is the so-called hybrid twin that I discussed previously. One example, some applications, and I'm finished. An example that is the flow of a resin in a mold. We need to solve this by using only data? Oh, no, because we know a lot of things about this. There are hundreds of years of science. There is one French guy that told Darcy that model the flow of a fluid in a porous media in something that is quite accurate. It's not perfect, but it's quite accurate. So finally, we know plenty of things. This is the knowledge. This is the art of modeling. And we know that we have a fluid domain, omega. The points inside are called x. The state of the fluid is defined by two variables, the pressure field P at each x and the velocity of the resin V at each x. And the relation between P and V is not necessary to discover from scratch because we have the Darcy's law that expresses that more or less the velocity is proportional to the gradient of pressure with a negative sign. That means that the fluid is moving from the locations in which the pressure is higher to the places in which the pressure is lower. And this K is the permeability tensor that characterizes the medium. And we know also that the velocity is not fully free. We know that the divergence of the velocity is zero because we have in the domain, in the fluid domain, the mass conservation. And finally, when combining both, we have this equation that is the divergence of K multiplied by the gradient of the pressure that is equal to zero. And we can solve this. This is the physics, and we can use a commercial software like, for example, in this case, PAM-RTM from ESI Group. And we are computing the volume occupied by the fluid depending on the permeability that is the parameter of our problem. And the permeability could be low, medium, or high. And now this parametric model, this virtual chart, is representing the evolution of the domain occupied by the fluid for different values of the permeability. This is only the visualization. We are not computing. This is the virtual chart. We are only visualizing the solution when choosing your value of the permeability. So this is physics in real time. As soon as the physics in real time is ready, we can take data in order to calibrate the model in real time. Calibrate means from the data, extracting the value of the permeability. But this is very easy. As soon as I detect with a camera the front, we use in order to check the best value of K in order to put both in agreement. So we can calibrate by using a level Marquardt technology, any procedure, this runs in real time, as soon as you know the position of the flow front for any value of K. You need only to select the value of K in order to be in agreement with the measurements. So this means calibration in real time as soon as you have data. But here there is not artificial intelligence. This is the Darcy's law, a parametric model that we compute by using model order reduction, in particular the non-intrusive PGD, and after a calibration procedure that proceeds also in real time. But I will try to express the necessity to introduce the correction. Why? Because at the beginning everything is good, but there is something that exists in the reality that does not exist in my model. When we approach the walls of the mold, the permeability reduces. And this is something that I know. By my parametric solution, ignore, there is an ignorance. My simulation thinks that the medium has the same permeability everywhere. And in the reality, I know that this is not the case. So at the beginning, no problem. Okay, I calibrate. Everything is perfect. Do you need artificial intelligence? Why no? The physics is perfect. I arrive here at the same instant. I'm very, very happy. But my God, what is this? I don't know. It's too late for me. I try to change, but there is no possibility. So finally, you have an ignorance. There is something in the reality that my model ignores. The hybrid twin. You remember? If one day there is a deviation, an ignorance, please model the deviation and continue. So at the beginning, do you need the hybrid? No, because the physics is enough. Do you need the hybrid? No, the physics is still perfect. And if one day there is a surprise, my model adapts. From the data, I compute the model of the ignorance. And I don't know why. Please don't ask me why. The important thing is my simulation is in perfect agreement with my experiment. I model the ignorance. Maybe in the future we need also to describe, to extract knowledge from the model of the ignorance. We are not there, but as I commented this morning, we are working on that in a lot of projects in order to understand all these things. Some now real cases in 5 minutes, and it's finished. Third one, batteries. We model all the electrochemistry in a battery, trying to solve it very, very fast. We use POD. After we create meta models, surrogates, the parametric solutions, by solving these models based on the POD very, very fast, and after we construct a surrogate, and the surrogate is able now to predict the evolution of the state of the charge and the evolution of the voltage as soon as you planify an itinerary in your electrical car. Now we take all this and we put all this in a system modeling, that is the system modeling of the electrical car, and we connect with OpenStreet in order to select, we would like to move from A to B, the origin point and the destination. And from that, we planify, we have a prediction, but as soon as you take your car, the circumstances, the traffic is a little bit different to the nominal ones, and this means that there is a difference with respect to your initial predictions. In this case, you take the difference, you construct a model of the difference, and like this, your previous model plus the model of the difference, this represents the reality that you are living. And like this, you can make better predictions by using this model. Second case, very practical. This is a problem, this is public. We are publishing a paper with Dassault Aviation in which we describe a system in the aircraft. But obviously, this is very complex. They are using system engineering in which all the components are 0D or 1D, and they are using Modelica in order to model the system that is very complex. So obviously, you can imagine that the prediction with this model with respect to the measurements are not fully in agreement. So this means that one prediction, as I indicate in the right part, when you are taking a prediction from this model and you compare with the data, you make the subtraction, one minus the other. If it's different to 0, this means there is a deviation. And this deviation, maybe there is a fault, and you can make diagnosis, for example, by using the TDA. If not, it's a simple deviation because this model is too simplified. And in that case, you are using again a physics-informed artificial intelligence in order to obtain the model of the deviation. And as soon as you have the model of the deviation, we apply the fundamental equation, something that is coming from a coarse model that is enriched with a model of the deviation. This represents the reality. And you can compare on the left the real data, that is the noisy blue and black lines with respect to the predictions of a model that is quite simplistic, but enriched with the model of the deviation in this hybrid framework in order to obtain the yellow and red functions that are very close to the reality. And this means with these predictions is better in order to make prognosis. In material modeling, you can assume that something that is complex, in this case, we generate synthetic data by using the Barlat yield with 18 parameters. And we assume that as soon as the data was ready, we assume that we take a simpler model like the quadratic hill. And obviously, with a quadratic hill, I cannot represent exactly the data, but don't worry. I'm using now an enrichment. The enrichment is we need to add the ignorance to the hill to represent Barlat. And finally, we obtain from the data something that we need to add to hill to finally represent the data that in that case come from a very rich Barlat model. So this is an idea of an hybrid modeling in the sense of determining an yield function related to problems in plasticity. Another example, and this is in the thermodynamic setting, you have data that is representing in the bottom. You have experimental data that are the blue circles, and we have a Money-Rivlin that is an hyperelastic model that we try to represent with this model the data. And obviously, I represent more or less, but not perfectly, because with a Money-Rivlin, I cannot represent a visco-hyperelastic model. And in that case, I ask to the thermodynamically consistent machine learning, please, can you add a correction to the Money-Rivlin? And the response was, in the conservative part, in the Hamiltonian, it's quite good. The only thing that I need is introduce a little bit of dissipation that does not exist in the Money-Rivlin. And for that, it computes a dissipation that corresponds to the viscous part in the behavior. And as soon as I add the correction, but in the thermodynamical framework to the Money-Rivlin, we obtain exactly the red line that fits perfectly the experimental data. So again, the reality is a first-order model that is not perfect, but not stupid, and some correction that I can learn quite fast, because finally, in this case at least, is smaller than the function itself. And for this reason, obviously, we can learn well and fast. And the last example, this is a bridge in which this is a foam. Obviously, we assume a model for the beam. the model for the beam, we are very far from the validity hypothesis of the modeling of this beam. And this means that by using this correction, by using the model, the solution was not perfect, but the system correct the beam model in order to obtain very accurate solutions. Last slide, and this is coming again from the team of Elias Cueto in Zaragoza, in which now we know data is okay. We understand how to compute models or solutions based on physics very, very fast. We know that if we compute very fast, but the solution is not perfect, we can enrich. And at the end, we would like also to have a dialogue between the virtuality and the reality. And this is the interaction between the human and the machines. And the thing that Elias is proposing is a kind of virtual mixed reality in which you have something virtual, the bunny, you have something real, the hand and the office. And now we are trying to interact with this virtuality. And here, there is not only geometry. This bunny is an hyperelastic material in large deformations. And we are using a kind of contact model in order to avoid penetration. We are moving in order to avoid this penetration. This is the Stanford dragon. We can touch and we can use the colors in order to enrich the representation. And so this is nice. Today is only visual. In the future will be multisensorial and emotional. This is our objective. But now, obviously, you can touch in the place that you want, and we can represent in real time. You can represent all the stresses in your system. So this is, and now the same on the right is very similar, but in that case, we are using holograms. And again, you have the Stanford bunny. We have the PGD that we are using in order to compute the different modes of deformation. And as soon as the modes are ready, you touch nothing. This is David and here. And now we're moving. Your bunny appears. And now you can touch it. It's only visual, but in the future may be richer. And now you can see we can start to create interactions between something that is virtual with something that is real. And this is very important, the first 3 lines in this slide, that people remember very differently what they learn after 2 weeks. 10 to 20% of what they heard or read, but 90% of what they did. So this means the future is not only to see. In the future, we need to touch. And in order to touch, we can create, and today is possible, digital twins, hybrid twins, virtual twins, the name that you want, but we need to create them according to the physics, real emulators of the real reality that can replace for something, some application, the reality itself, and we need to discover a new way to interact with them. Last, we are moving to an intelligent hybrid intelligence based knowledge, data. There is not a problem of opposition. We need to create, obviously, an alliance of them. We are moving to the performances by design. You remember, we need to augment the human, and at this moment is quite visual. We are working now in the multisensorial and emotional dimensions to empowering humanism, and obviously the things that is new, we need to compute fast and well, because we are not in the art of modeling. This was in the past. We are not in the art of simulation. This was in the past. We are in a new art of the engineering, that is the art of the decision making. And for that, obviously, we need to create a new framework in order to make a definitive alliance between these 2 worlds that are fast and accurate. So this is all from my side. Thank you very much for your for your participation. And obviously, if not today, because it's a little bit late, I'm really sorry. Don't hesitate to send questions, to contact me if you have questions, and I will provide papers, the presentation, or respond to all your questions. Thank you very much.